Hi, welcome to MediQuarrier. Please like our videos, leave a comment behind, subscribe to our channel, turn on your notifications, and share this video with all that stand to benefit from it. This is the third part of our introduction to medical imaging. Today we are going to discuss how X-rays are produced to the X-ray tube. The X-ray tube is enclosed in a glass envelope. Much of the surface of this envelope is coated with lead, except at the window where the X-rays exit the tube. The glass at the window of the tube is sometimes replaced with beryllium, a metal which is more transparent to X-rays than even glass, owing to its low density. At one end of the X-ray tube is a filament which is made of tungsten. When this filament is heated, it produces electrons by thermionic emission. Tungsten is the metal of choice because it has a very high melting point which is able to resist the high temperatures in the X-ray tube. All the materials used in the construction of the X-ray tube have the property of being able to resist high temperatures. Surrounding the tungsten filament is a concave-shaped focusing cup made of nickel. A strong negative charge is applied to the focusing cup, which repels the negatively charged electrons and focuses them to a tungsten target on the anode. The anode, on the other hand, has a strong positive charge applied to it, which attracts the negatively charged electrons, which interact with the tungsten target to produce X-rays. Now let's dive into talk about the actual production of X-rays. An electric current is applied across the tungsten filament, causing it to heat up and release electrons by thermionic emission. The higher the current, the more the electrons produced. The electrons are repelled and focused on the tungsten target on the anode. The electrons strike the tungsten target at the anode at a very high velocity, converting 99% of their energy to heat, which is dissipated in the cooling system, and 1% of the energy is converted to X-rays. X-rays have a frequency between 30 petahertz and 30 exahertz, a wavelength between 10 picometers and 10 nanometers, and an energy between 124 electron volts and 124 kilo electron volts. We'd earlier on mentioned that X-rays are produced when the speeding electrons interact with the atoms of the tungsten target, producing two types of X-rays: Bremsstrahlung radiations, which are the majority, and characteristic radiations, which are the minority. The word Bremsstrahlung comes from two German words which mean radiation that is produced when the electrons break. This type of radiation is produced when the negatively charged electrons are decelerated by the positively charged nucleus of the tungsten atom, losing their kinetic energy. Bremsstrahlung radiations contain X-rays of varying wavelength because the wavelength depends on the amount of kinetic energy lost by the speeding electron. Characteristic radiations, on the other hand, are those X-rays whose wavelength is typical of the metal used as the target at the anode. For example, tungsten produces characteristic radiations of a particular wavelength, whereas another metal will produce characteristic radiations of another wavelength. These radiations are produced when a speeding electron knocks out another electron from its shell, followed by a replacement of that electron by another from an outer shell, which loses its energy and produces X-rays. The X-rays produced are of a particular wavelength because this corresponds to the difference in binding energy between the shells involved, as we shall illustrate shortly in the diagrams. Let's start with the Bremsstrahlung radiation. So here is our metal atom at the target, and here is our electron from the cathode. The electron is accelerated towards the target, and as it nears the nucleus of the metal atom, it's decelerated, losing its kinetic energy, most of which is dissipated as heat, and 1% is converted to X-rays. This electron can be completely stopped, or it can proceed to interact with another nucleus. The production of characteristic X-rays involves collision between electrons. The electrode from the cathode is accelerated towards the atom. It collides with an electron in the atom and displaces it from its shell. An electron from a higher shell then drops into the empty shell, losing its kinetic energy, which is converted to heat and X-rays. Now that we have an understanding of how X-rays are produced, let's go on to look at how they interact with the different tissues of the body and how the X-ray beam can be modified. X-rays that are strong enough can penetrate through the body and can be used to form images of the internal organs of the body, either on a film or on a computer screen through digital processing. On the other hand, X-rays that are weak are absorbed completely by the body tissues. Therefore, they do not penetrate through to reach the film and do not participate in image formation. In other words, these X-rays only add on to the patient exposure but without any benefits. In order to prevent unnecessary exposure of the patient, we use an aluminum filter to filter out these useless X-rays. As the X-rays pass through the body, some of them are scattered by the tissues, especially in fat people. This phenomenon is known as Compton scatter. These scattered X-rays disorganize the image and make it unclear. A grid made of lead is placed beneath the patient to absorb these scattered radiations so that we can end up with a clearer image. Knowing about the harmful effects of X-rays, it is important to limit the exposure of the patient to only the field of interest. This is achieved by the use of a lead collimator, which limits the X-ray beam to only the area whose image is required. On top of limiting the dose of exposure, collimation also has the advantage of reducing Compton scatter. I want to thank you so much for listening to me till the end. Please help my channel grow by liking my videos, commenting on them, subscribing to my channel and turning on your notifications, and by sharing my videos with your friends. Feel free to ask questions in the comment box below or to request for a video on any particular topic of interest as long as it's medical related. Alright, catch you next time.